predicting waiting time, multiple identical parallel servers. If we want to generalize our model that predicts waiting time to multiple servers, we can consider multiple parallel servers, all of which serve the same stream of customers, but there are several restrictions. All servers have to be identical, so they have to have the same average service time and the standard deviation of service time. They all have to work in parallel, and customers have to be waiting in one waiting line. There's a different symbol here for waiting line that is used. And basically, the moment one of those servers becomes available, when the customer leaves the system, the first customer in the waiting line immediately jumps into the server, so the customers do not have any preferences for the servers. So all the other parameters are the same. The only generalization is there are multiple servers here. They are identical and they work in parallel. So they have all the parameters that we defined before: average inter-arrival time, average service time, coefficients of variation for CV and for inter-arrival and for service times. All of them have to be defined. But in addition, we need to define M, which is the number of servers, right? So before M was basically equal to 1. Now we can consider one or multiple servers with this model. We also have to update our formula for utilization. Before, when we calculated, it was flow rate over capacity, and flow rate was 1 over A, capacity was 1 over P, but because now we have M servers, in fact, our capacity, we can process M customers every P time units. So our capacity is M over P, and if you simplify this formula, you get P divided by A times M. And so average waiting time, as before, is defined as a service time factor, kind of, multiplied by utilization factor, multiplied by variability factor. But in this case, there are two changes. First of all, service time is divided by M. So this first component is divided by M. This is average service time. The kind of service time divided by the number of servers. And the second change is that in the utilization factor in the numerator, instead of having just U, we have here U to a certain power that depends on M. And this power, basically, as M grows, the power will be also growing, but in a nonlinear way. So if you see here, if M is equal 1, actually, 1 plus 1 will be 2, times 2, it will be 4. So we'll have square root of 4. That will be 2. And then subtracting 2 minus 1, we'll get 1. So basically, for M equal 1, this factor, this power here for U will be equal to 1. But if M is 2 or 3 or 4, there will be some other numbers more than 1. Everything else is the same. So we have division by 1 minus U. We have the variability factor calculated in exactly the same way. As before, we can calculate all kinds of parameters here, right? Flow times or inventories, assuming, right, the flow rate is known, and we have TQ to start with. And then what else? Of course, we're assuming still a stationary process, and we're assuming utilization or implied utilization are both less than 1. If not, again, don't expect this model to work. In fact, you can see that if you divide by, if U is 1, there will be a division by 0 here. 1 minus 1 will be 0. And if U is, of course, more than 1, if implied utilization was more than 1, then this model would actually give us a negative average waiting time, which wouldn't make sense. And the reason for this is that the model actually doesn't work for implied utilization more than 1. We know without the model that the average waiting time would be infinity. Final note to this model is that the formula for this waiting time is an approximate one. There are more accurate models, but they're much more complex, so I'm not introducing them here. This model is especially good, especially accurate, if you have very high utilization and relatively low number of servers. For a larger number of servers and the low utilization, the formula is not that good. So let's consider an example. Suppose now in the same service that we considered before with 1 server, we now have 10 servers, and now we have much more demand, right? Before we had 3 calls per 15 minutes, now we have 79 calls every 15 minutes. So a much larger number of customers calling us per 15 minutes. And suppose service time is still the same, 90 seconds on average, standard deviation, 120 seconds. So let's do some calculations. First of all, let's calculate average inter-arrival time is, we can calculate it as 15 minutes. Every 15 minutes, I have 79 calls. So on average time between calls will be this in minutes. Well, I can convert this to 900, right? 15 times 60, that's 900 seconds over 79. That will be in seconds. And so I can calculate this as 11.39 seconds. I can calculate the average processing time. Actually, it is given 90 seconds. And also, I know CV of A, the coefficient of variation for inter-arrival times, is still 1, assuming exponential inter-arrival times. And CV of P, as before, it is 120 over 90, the given standard deviation over the given mean of service time. That will be 1.333 if we use 3 digits after comma. Now we can calculate also utilization, and recall that utilization is processing divided by two things, right? By average inter-arrival time multiplied by number of servers, right? So if I do this, let me plug in the numbers. It will be 90 seconds divided by A is 11.39, and this is 10. So the utilization will end up being 0.79. And notice that this is less than 1, which is important, right? So we can use the model, right? The model will work. Remember, this is very important assumption. Before you apply the model, you have to check this. So now we are ready to calculate the average waiting time with the TQ formula that we presented before. So if you have this formula, if we plug in the numbers, notice this will be 10 here, 10 plus 1, 11 times 2, 22. There will be square root of 22. We need a calculator or Excel or some kind of sophisticated calculator to be able to calculate this. Be careful, -1 is after the square root, right? And don't forget to divide P by M here this time. That's the two, these are the two differences. So if you do the calculation, right, we're going to get 90 over 10 here, times the factor here will be 1.995, and the variability factor will be 1.389. Actually, it's the same as before, and that will give us 24.94 seconds after slight rounding. So notice, despite the fact that the utilization is now much higher, right? The waiting time is actually quite reasonable. It's actually around half of what it was before. And the reason for this is that we have now 10 servers, quite a large number of servers, and there are actually some economies of scale here. If you have a lot of servers, even with high utilization, you can have low waiting time. We can calculate other things. We can calculate the total time and system as TQ plus processing as before, 24.94 plus 90, which will be 114.94 seconds. And the same way we can calculate inventory, right, which will be TQ, the inventory number of customers waiting, multiplied by the flow rate, which is 1 over A, right? So we can still calculate this as 1 over 11.39 times TQ, which we calculated as 24.94. If you do the calculation here, you'll have 2.189 units waiting. So on average, there will be slightly more than 2 customers waiting. Notice this should not be rounded to 2 or anything because a fraction matters here. Average can be fractional even if the actual values are not fractional. IP, number of customers being served on average, will be same as before, right? 1 over A is the flow rate from Little's law multiplied by flow time, which is P, right? So again, it's the same value here multiplied by the flow, by the processing time 90, and that will give us equal to 7.9, right? And notice, so there is on average, on the servers, we'll have on average 7.9 customers. And this is again not surprising. If utilization is 79%, then on average there will be 7.9 customers in 10 servers, right? And again we can calculate, for example, inventory as a whole, right? It could be I inventory and processing plus IQ inventory and waiting. So there will be a total of around 10 customers, 10.089 customers present in the system. Or you could think about the number of lines that will be occupied by all those phone calls, because remember, those customers do not show up physically, they actually call us. The number of lines occupied will be 10.089 on average. And remember, this is again an average. So there could be much fewer or much more lines. We might actually have 30 lines occupied at some point. It is also possible.